Scheduled discussion. We have 3 chairs, Daisuke, Nir, Charlotte.
So we're going to start the discussion session. We posted some Google Docs, so you can go to the program and you can click, and there are a couple of guiding questions that we formulated, but we can also, of course, open up the questions for and solicit questions from the audience here. So we have sort of 3 general topic. First, maybe you can start with the first thing, questions on CGM, IGM, followed by questions about how the cosmic web impact galaxy properties, and then the third topic would be about the impact of cosmic web, maybe looking for connection between the first set of talks to then the impact on halo galaxy gas connections. We don't have to be restricted to those questions. I also like to encourage junior colleague to give a little bit of pause and then allow junior colleagues to ask questions as well. So maybe let's get started with the first one. I think that's going to be Nir will help lead the discussions, followed by Charlotte, and myself will cover the topic 3. So let's get started.
Okay, thanks. So we heard a few talks today about kind of very small scale structure in the circumgalactic medium in the cosmic web. The word shattering was thrown around here a few times. And with no cosmological simulations that enhance the resolution in the CGM and also in the IGM more and more. I'm talking about the foggy simulations, the tempest simulations, similar efforts by our group, UC-HiPACC, and there are at least maybe 5 or 6 groups. The more you increase the resolution in these supposedly uninteresting diffuse regions, the more and more small-scale structure you get, and convergence doesn't really appear to be anywhere in sight in the cosmological simulation. So a few of the questions are, what are some of the more robustly predicted properties of the circumgalactic medium and the intergalactic medium? How can we really trust these in cosmological simulations? What extra physics might we need to consider in order to get convergence in the simulations? Cosmic rays, magnetic fields, thermal conduction, these are all going to be affecting these. Are these really becoming very necessary to include in the simulations in order to get the phase structure of the circumgalactic and intergalactic medium correctly? And then perhaps tying it back into the observations, what observations do we need in order to constrain this? Cloud sizes, cloud densities, thermal to non-thermal pressure ratios, etc. And at the end of the day, assuming that we can say something meaningful about cold gas in these environments, are these going to teach us about accretion from the intergalactic medium? Are these going to teach us more about galactic outflows going farther out, or thermal instabilities in the circumgalactic medium? What are people's thoughts about this? Feel free to address any of these or anything that you might like.
Well, so I've been struck by the disconnect between people who study the CGM and people who study galactic winds, in particular with regard to what the word cold means. So people who study the CGM consider 10 to the 4 Kelvin cold. But if you actually look at resolved galactic winds from, M82 is the poster child, most of the mass flux is in atomic and molecular gas, not 10 to the 4 Kelvin gas. And that seems to be true of a lot of at least starburst winds. And so that seems to me like something that's, if you want to, I don't know about converge within the simulations, but if you want the simulations to be able to say anything to observations, it seems to me like a key missing piece of physics are the processes that control the phase transitions between the atomic, molecular, and ionized phases. I mean, an obvious question to me is like, well, all right, we see the mass coming out of M82. It's all to first order atomic and molecular. I presume at some point, somewhere, somehow, that switches to ionized gas, because there's probably not a lot of molecular or atomic gas floating around in the CGM. Where? When? That seems to me like a key question that a lot of this stuff is ignoring.
I fully agree with Mark, but I had another thing I want to mention. This is that I agree that they are not converged in cosmological simulations, but not all simulations are cosmological. And it depends on the, there are some physical scales that will set the convergence. It's just that we're usually not reaching them in cosmological simulation, like the cooling scale. So if you reach the cooling scale, then you can converge in some aspects. If you include thermal conduction, the thermal conduction will set a scale. And so once you reach that, then you imagine that some of the results will converge. The problem, in a sense, is that most of the scales are parsec or less than a parsec. So it's not that you never converge. It's just that it's still very unfeasible unless you do really super resolved toy. So I think we have some predictions from those models, and you are doing some of those. So.
So just to quickly follow up on that, would that imply that if we want to use simulations to study the circumgalactic medium and compare them to observations and use them to constrain galaxy formation models in a meaningful way, is there no choice? Do we have to include thermal conduction in our simulations, and we should throw away any simulation that doesn't include thermal conduction because it will never converge? By a show of hands, who thinks we should throw away any CGM simulation that doesn't include thermal conduction? Okay, that's good. So we're all in business. Oh, okay, I see one.
Yeah, I think in light of Mark's question and a serious problem that I think you've posed, and I'd like to come back to what Habitable Worlds Observatory can do for you. And so one of our second science case is looking at the disk halo interface, and in particular doing a search for molecular hydrogen and absorption at the same time that we can cover some of these other species that typically trace 10 to the 4 Kelvin gas. So the idea is that we could actually see all of this stuff kind of in context with one another. So to directly address that, I think there's some strong potential there, particularly if we can go down to 1,000 angstroms coverage, low redshift galaxies, the nearby galaxies.
I'm certainly a fan of H2 in absorption, but I do worry that that is problematic because probably the covering fraction is small, even though it's most of the mass flux. So I worry about doing in absorption. It might be very hard just because, right, molecular clouds are 30% of the mass of the ISM at the solar circle, but they occupy 5% of the area of the disk and 1% of the volume. So I worry that an absorption-based technique is going to have trouble. Okay.
Short comment. Mark, you said that, look at M82, you said you see mostly molecular and super cold gas. I mean, the thing that people see is in fact the red stuff, which in fact is H-alpha. So, and then Alton Coyle, for example, showed us O2, for example, is a wonderful emission probe. So those are all.
Maybe we should move on to the second topic out of 3 to keep on time.
So the second topic relates to all the talks we had on the cosmic web, who investigated the effect of different types of filaments on galaxy properties. And so the general question is the one as old as cosmic web studies. What's the impact of cosmic web on galaxy properties for both stars and gas? But in particular, I'd like to refine that a little bit. We have identified a number of properties that are affected by distance to filaments or belonging to a filament. And we tend to say things like the effects are small, and more I'm worried that it's small because we are stacking lots of different types of filaments with different types of dynamics. So the problem, as I said it, is the cosmic web environment involves many definition of scales, which do not easily or consistently correlate to specific type of filament dynamics. And I really love this plot by Joanna, where you have a thickness defined based on density profile versus density. And you have a correlation, but somehow the scatter is pretty much as big as the correlation itself. And if you try to add another definition of scale, then it's all over the place. In that range, you go from high to low length. If you go up there, the trends seem to reverse. If you look at low filament density, fixed density, as you increase thickness, you decrease length. And if you go at a high filament density, you see the exact opposite. So, and it's very common when we try to define scale by different parameters. It goes all over the place. And the underlying thing that's happening is probably that we have different dynamics. So my question for you is, how do we disentangle those scales to better sort out filaments in categories where we can then relate those to galaxy properties? Or how many parameters do we need to describe a filament, and how do we test that in observations on different type of galaxies? And I'll just add a second question. If we're talking about filament dynamics, how do we better track filaments on various scales? Have we converged on the fine structure of filaments? Related to CGM, do we know which filaments pervade in which halos and how deep? And can we define new ways to track filaments, more of them across cosmic time?
David again. Just a general question. I think of filaments as largely a gas phenomena, and yet we as observers, of course, can see only galaxies today. But I think in the future, and with work like Sebastiano, that there's going to be a lot more gas information. I think you may want to redefine what they call filaments that have been talked about during this week versus filaments in the near future. In fact, using gas as being the definition, not that of galaxies.
I just want to clarify that the plot that I showed was for gas. So those the thickness and densities were gas densities and thicknesses, but they were found on the basis of the slime mold model, where the galaxies are the tracers of the filament. So it's the tracers are the galaxies, but the properties that I showed here were for the gas.
Should potential wells be then used, since you have the simulation, so you know everything, right? You don't need to use stars as being the basis. The small galaxies have a lot more gas component versus the stellar component, which is a different process.
So the results are presented. The filaments were extracted on the gas uniquely. This was purely gas filaments. But as we discussed with some of you earlier this week, the problem with gas is that it's hard to consistently identify filaments at small scales, because methods like disperse are based on persistence, which is a contrast between critical points, which trends with densities, but not always in the same way. And in particular, it trends really well with density in dark matter, because dark matter is self-similar down to small scale. But gas is not self-similar down to small scale. And if you try to extract gas filaments at small scale, you need to adapt a bit the method, which makes them maybe less comparable.
So I was thinking about, so what I've found is that the gas properties are they follow the dark matter properties pretty closely, except for different scales and density and mass. But I think your question is a good question. How do we define a filament? I think we can take inspiration for how do we define a halo, and we normally do that as a certain, delta above the mean density of the universe, some like 200 or something. And we can define filaments based on some sort of density above the background.
Yes, but they are not collapsing structure. Not all of them. That's the issue. Some are collapsing, some are stretching. I think that's the main issue. And maybe in terms of different dynamics, that's why we would need more parameters.
Yeah, I just want to add that I think there's differences in at different cosmic times, right? So at higher redshift and at lower redshift, you're gonna have different average like thicknesses and lengths of filaments and really gas properties, all that kind of stuff. So even trying to define filaments in terms of like for example setting a length threshold or thickness threshold, it's gonna change so much with redshift, and not all filaments are the same, and not all filaments of the same properties or same lengths and widths at different times are the same. So it's not an apples to apples thing, pretty much.
Not to be that person who answers a problem with another problem, but I think we could also take a book out of ISM science. There's a chapter in Planets and Protostars 7 that came out last year that essentially has this entire chapter dedicated to filamentary structures in the ISM. And now a lot of ISM filamentary science uses a lot of algorithms used to study the cosmic web. So for example, disperse. But there's an entire section in there about sort of the numerical biases that are sort of assumed in a lot of these filament finders. They sort of, select only for structures with a particular aspect ratio, certain things like persistence, for example. And if you've ever opened up like an ISM textbook about filaments, there's like 10 different types of like filaments you can just like define in the galaxy, ranging from all kinds of different scales. And there's currently like an ongoing effort in ISM science to find a better way to define these ways, or define methods that can identify filaments in a sort of bias-free way, but at the same time be specific enough to tackle like particular problems. Like, yes, I only want to look at things that are sort of on a scale that are relevant to the science that I have, but at the same time, like, do I want to discriminate between something that kind of looks like a circle versus like something that has a filamentarity that looks like a line?
Yeah, so that would boil down to having more parameters to segregate filaments, right?
So Peter Bruce here. I'm with Joanna on this one because I feel like you can always add tons and tons of more properties that you calculate for filaments, like collapsing or stretching. But having a definition that everyone agrees on is very simple to calculate has been very, very useful for halos, and I feel like the same thing would be true of filaments. So whatever definition you prefer, if you also give a density-based definition, then people can cross-compare across studies in a way that they can't do easily right now.
So there are endeavors towards defining the thickness as a splashback radius, like it's done for halos. And I think it's working quite well, but precisely when you do that and you try to put that against some other physical definition of thickness, like the edge of the vorticity whirl, or the position of an accretion shock, then these do not correlate very easily. So that's Yeah, it's good, and there is value in having simple density-based definition that looks like halo. But in practice, I think we're already seeing on the hydrodynamics the effect of different dynamics showing at scales where that matters for galaxies.
Yifei from CFA, and this might be a very naive question. So, from the purely observational side, if we just observe the filament, the gaseous filament, by using the quasar nebula, will it bias to the very deep potential wave and with the with the quasar inside, and will the sample to bias to this kind of environment? So, how to disentangle the effect of the potential wave itself or the filament itself? So, which will be the first driver? It might be a kind of thing I think we need to think of.
Okay, we have 5 minutes left on the clock.
Okay,
Maybe we
so
want to
thank you for this nice discussion. Maybe
topic
we'll
3.
touch
Okay,
to
so
topic
let's
3
move
on the
on
halo
to
gas
the
galaxy connection.
So I think we had a talk also on the halo galaxy connection, and maybe make a connection to the previous topics. Maybe one possible discussion topic would be, what's the impact of cosmic web that we've been talking about? How would that affect the halo galaxy connection? Maybe the other aspect is that there is this halo galaxy connection. There's also halo gas connection. We've been talking about CGM, which is a gaseous medium that's also baryons that's sitting inside of dark matter halos. So would this be a good time? Are there a path forward in building or some sort of unified model of dark matter halo gas and galaxy connection that are a little bit more self-consistent? Maybe this is the time for us to start thinking about developing something a little bit more unified. So maybe those are the questions. Maybe the floor is open.
So Sandy Faber, I think we all agree that 3 important parameters for galaxies are stellar mass, star formation rate, and radius. And we've had a lot of discussion about how radius might come or originate from angular momentum, and whether that's a very predictable thing. A problem with star formation at any rate today is that the star forming sequence has some significant width, and I don't think we've found out any way of explaining that. So I'm just worried that 2 out of these 3 numbers have a sort of stochastic element to them, and I think we should be thinking about influences from the halo and the web that would be persistent over time, and identifying those forces, because galaxies are not completely chaotic. We need some orderly evolution of processes over time.
Aldo Rodriguez. Yeah, the important point about the semi-empirical modeling is that those models are driven by data. We have very few data. So, for example, including the gas it's being hard because even at redshift 0, we have very few data for H1 and H2 gas passes. So we have the cold gas sample, which is around 100 of galaxies. We have alfalfa, which are 10,000 galaxies. But those are very few samples to really understand how we can include the gas mass or understand the baryonic sample through the semi-empirical modeling. So I guess that in the future with SKA, we will have more data to get that, but that will be only H1. The problem will be how are we going to include H2 observations into the semi-empirical modeling.
Maybe one thing I can probably add, like looking forward into the future, is that there may be a warm and hot phase that could be probed. So far, the absorption line has been the main probe for studying those phases, and you can only see sight lines. But I think there has been increasingly more measurements of hot, warm gas for example, by stacking X-ray measurements from Erosita, stacking SZ measurements from FRB is providing complementary sight lines. So maybe these might provide some additional diffuse warm hot gas, which has never really been used so far. It's only becoming available, and over the next maybe a few years, we can get more of those observations. So maybe keep our eyes out for those observations, which might be useful for constraining. Right now, I think we can basically the cosmological simulations that are tuned to reproduce stellar mass halo mass relation, for example, are making predictions for what those hot warm phases are, and they are very different in terms of prediction. Once the data comes online, some of the models can be tested, ruled out, and then we can refine the subgrid model by taking advantage of those warm hot phases as well as cold and molecular phases as well. So maybe that's something to look forward to. Maybe too early on, but maybe in the next few years, maybe we can discuss more of this in the future. So maybe I think I realized that the time is running out. So I think this is a good time to maybe stop. And so thank you very much for all of the speakers and all of the discussions today.